Lesson 6.6 continues with solving exponential and logarithmic equations. We'll use our properties for change of base, and we'll also use our quotient, product, and power properties. When asked to solve exponential equations with a common base, we apply the rule that a to the x power would equal a to the y power if x equals y. And that should seem reasonable. If your base is the same in an equation, your exponents would have to match as well. Now in this set of examples, we're going to want to make a common base, which means we're going to likely need to work with our power chart. And as we work with our power chart, our goal is to make the bases the same. We start off with a pretty basic one. 4 to the x power is equal to 16 to the x plus 3 power. Looking at our two bases, we have a base of 4 and a base of 16. Now we've done this before, and our goal is to make the big base become smaller. That way we don't change what the equation means, we just change what it looks like. I know that 16 can be rewritten as 4 squared. I didn't change the equation, I just changed what 16 looked like. And then I have to put it to the x plus 3 power. On the left, we already had 4 to the x power. Oh, and I can't get that even to fit in there. All right, let's try that again. 4 to the x power. There we go. Now, on that right-hand side, with the 2 on the inside and the x plus 3 on the outside, I need to distribute that in. That will give us 4 to the x on the left and 4 to the 2x plus 6 on the right. And now that our bases match, the rule is going to be to work with their exponents. A to the x equals a to the y if x equals y. That means this equation can only be true if x is equal to 2x plus 6. Now we just need to solve for x. If I move 2x to the other side, that gives me negative x is equal to positive 6. Therefore, x will equal negative 6. So in this example, we just had to change one base to get it to match the other one. That won't always be the case. Let's move on and try example B. In example B, we have a base of 36 and a base of 216. Unfortunately, we cannot change the big base to be a power of the small base. If you look at your power chart, however, you can see 36 and 216 in a common row. They both can be rewritten as a base of 6. That means 36 can be rewritten as 6 squared. We would have to still raise that to the 2x plus 5 power. 216 could be rewritten as 6 cubed. Oops, that's a 3. And then we'd have to raise that to the 3x power. And just like that, in that one step, the bases are the same. Let's clean up their exponents. The 2 with the 2x plus 5, if I distribute the 2 in, we would get 6 to the 4x plus 10. Maybe. We'll try that again. Just starting all over. All right. 6 to the 4x plus 10. Ah, goodness. All right. Well, that's as good as that's going to get. And on the right-hand side, 3 and the 3x, if we multiply them, that would be 6 to the 9x power. Now that the bases match, we'll simply set the exponents equal to each other. 4x plus 10 should equal 9x. Combine like terms, I'll move 4x to the other side. That's a 4. Oh, wow. 10 equals 5x. Okay, this is getting better. Here we go. You should get x equals 2. And that solves that exponential equation. Now the last one's even trickier yet. We have 1/2 to the x plus 7 equals 4 to the 3x. Well, I see a base of 1/2 and I see a base of 4. Thinking about how they can compare to each other, 1/2 is the same as 2 to the negative 1 power. because that just puts the base then in the denominator. And we'd still have x plus 7. That's helpful because on the right, 4 can be rewritten as 2 squared. So notice I haven't changed the meaning of either side, we just kind of changed the format of what it looks like. Thinking about that process, now we have the bases that match. We just need to figure out what's going on with their exponents. For the left-hand side, if I distribute the negative 1 in, we would get 2 to the negative x minus 7 power. On the right, if we multiply those two together, we would get 2 to the 6x power. Once the bases are the same, we simply set the exponents equal to each other. Negative x minus 7 equals 6x. Simple enough, let's move x to the other side, and we get negative 7 equals positive 7x. Divide both sides by 7, and x will equal negative 1. That's solving by finding a common base. Sometimes when solving these equations, it's not possible to find a common base, so we use that change of base formula. Along with that, we can apply what's known as the property of equality for logarithmic equations. For the example on the right, it says rewrite the equation using logarithms. What we can do with an equation that's exponential, instead of looping, is we can actually just do the same operation to each side. That means I'm just going to take the log of each side, and that's applying that property of equality. What you do on one side, you do to the other. If we do that, it'll look something like this. Instead of 17, I'm going to take the log of 17. And then instead of 4 to the x, I'll take log of 4 to the x. When you convert this equation to logarithmic by taking the logarithm of each side, what that can allow you to do is take that exponent and apply the power property and put it out in front. That would give us log 17 equals x times log 4. And once x is out of the exponent location, we can divide by log 4 to get x by itself. And that's ultimately the change of base property. Plugging this into your calculator, x would be approximately 2.044. That's what would happen if you have just one exponent. When you have bases on each side of an exponential equation and you can't get them to match, this is what we would call uncommon bases, kind of like the example up above in 2a. What we'll do is we'll just take the log of each side. We'll apply that property of equality. From there, we'll have to apply our other properties and simplify. Be careful with your order of operations here. If it says, what is the solution to 3 to the x plus 1 equals 5 to the x, 3 and 5 don't have a match on our power chart anywhere. So I don't know where that line's coming from, sorry. So like I said, you're going to want to take the log of each side. And we literally just write log, and then 3 to the x plus 1 equals log 5 to the x. When we log each side, we now have converted the logarithmic part of the equation to base 10. So this will be calculator friendly. From here, apply the power property and put that out in front. But because this one has a sum with it, we need to put that in parentheses. X plus 1 times log 3 equals, take this exponent, put it out in front, x times log 5. Now our goal is to get x by itself. So we could either move the log 5 over or the log 3 over. But when we do, we need to divide. I'm going to actually move the log 3 over. That way we don't have to distribute it in to the parenthesis. Now on the left-hand side, it will in fact cancel out, leaving us with x plus 1. On the right, if we actually divide log 5 divided by log 3, we would get approximately 1.465 times x. So now we need to get x by itself. Notice there's 1 on each side. I'll move the x over on the left to match on the right. And that leaves us with just 1 on that left-hand side. On the right, if we have 1.465x minus x, that would give us a coefficient of just 0.465. To get x by itself, we'll divide. And I'm going to the nearest thousandth. Just be mindful of the directions on Pearson as far as your rounding rules. If we take 1 divided by 0.465, we get approximately 2.151. That would be the approximate value for x. That's a solution to the equation with uncommon bases. And last but not least, we'll end our lesson today with some application. It says the diagram shows how a forest fire grows over time. So as you look to the right, initially it starts off with burning 4 acres, and then it goes up to 7.2, 12.96, and 23.3. So it escalates pretty quickly. It says the fire department can contain a 160-acre fire without needing additional resources. About how many minutes does it take for the fire to become too big for the fire department to contain without needing those additional resources? What we need to do is figure out an equation that represents how quickly the fire is burning. Using the information over here on the right, it says at time 0, we burn 4 acres. Over time, the acres increase. So then it would be in 1 minute of time, it goes up to 7.2 acres. In 2 minutes of time, it goes up to 12.96 acres, and so on. This is going to be exponential. What we need to do is figure out the model for, I keep drawing that weird line, sorry. I don't know why I'm doing that. Okay, what we need to do is figure out our exponential model for this equation. So thinking about exponential models, we know that the template is y equals a times b to the x power. A would be the original amount that's burned, b would be the growth factor, and then x would be the time. So if we think about that first number right there at 0.4, that means when they get to the fire, there's already been 4 acres that have burned down. So A will equal 4. And I'm sorry, my cat is talking to the birds again. She's very excited about it, so we're just going to let her go. If I substitute 4 in, we need to then figure out what that growth factor is. That means I'll pick another value for x and y. I'll just go to the next point. After 1 minute, 7.2 acres of fire have burned. So that's your x value and your y value. If I substitute those in, that will help us determine what our b value is, or our growth factor for the amount of the burn for each minute. If we divide both sides by 4, b would equal 1.8. So that fire is burning pretty quickly. It's almost doubling the number of acres per minute. If we substitute b back in, then our general formula to kind of model how quickly the fire is burning would be y equals 4 times 1.8 to the x power. Now x is time and y is number of acres burned. We need to know that for the second part of the problem. We were asked to determine how long it would take for the fire department to not be able to contain the fire, meaning how long will it take to get to that 160 acre value. That means we're going to plug in 160 for y, and then we have to work backwards. If I set that equal to the formula on the right, that'd be 4 times 1.8 to the x power. Now this is just an exponential equation. Notice we've got 4 times 1.8 to the x. That means we have to divide the 4. The 4 isn't the base, it's just that coefficient out in front. 160 divided by 4 is just 40. And now that your base is isolated, we could convert to logarithmic, or we could just apply that property of equality and take the log of each side. If we do that, it just kind of saves us a step. Once you logarithm each side, you can take the exponent and put it out in front. And that would give us log 40 equals x times log 1.8. Now, to get x by itself, we just need to get rid of that log 1.8. I'm going to slide that up a little bit. That means we'll divide. And now remember, x is standing for time. Go ahead and plug this in to your calculator. If we take log 40 divided by log 1.8, we get approximately 6.276 minutes. So it doesn't take very long for that fire to escalate quickly and burn over 180 or 160 acres. It says about how many minutes does it take? We would say about 6 minutes. After that amount of time, that fire, if it's not contained by the fire department, would burn quickly, and they would need additional resources. That's it for today, you guys. Please take a picture of your notes and send it to me for credit.